Hi everyone, welcome back to the lectures on electrodynamics, and this is the 8th of the series, and our main reference is again Introduction to Electrodynamics by David J. Griffiths, and this book is recommended for you. And by the way, I hope it's recommended, by the way, to watch this lecture in parts, not in one sitting, because it will be very hard to mentally digest everything. So it's recommended you watch this in parts. So for this lecture, we will start with divergence and curls of electrostatic fields. We know what electrostatic fields are. First one we know is the electric field, and this is caused by some charge that's settled in space, and this charge radiate electric field throughout the space. So for a single point charge Q situated at the origin, just say an origin where everything is 0, 0, x equals 0, y equals 0, z equals 0, or the radius is equal to 0. So you have this electric field coming out or coming in towards the charge, or coming out towards the charge. If it's positive, the electric field goes out of the charge. When it's negative, it's going into the charge by convention. So this is the electric field. So this is the electric field, and you have the electric field is given by, the magnitude of the electric field is given by 1 over 4 pi epsilon sub O times the charge, so over the distance square. So if you measure the electric field at some point, so if you have a charge Q in this so let's just adjust this. So if you have a charge at this point and you are measuring the electric field at some point here, P, so if this is a positive charge, then at point P, the electric field will just be in this direction. It's along the line joining the charge and the point. Here there is no charge in this space. For example, there's no charge. You only have one charge in space, and this charge is radiating electric field. At this point, it's like weaker. Then at this point you have a stronger electric field, because it's nearer to the charge. And so when it's nearer, it's stronger, and when it's farther, it's weaker. And if the charge also is large, the electric field would also be large. And if you have a very small charge, then the electric field will also be small. Here you have an electric field. Yeah, of course you have a point charge here. So when you go farther away, the electric field will, the magnitude of the electric field will get smaller. And by the way, we can also represent the electric field to be a continuous line with radial direction coming from the charge. So it's assumed here that the charge is positive, so it's going out of the charge. And if the charge is negative, the direction of the field will just be opposite to this. So when you have a negative charge, say for example negative Q, then the electric field will just have to go inside, I mean converge to the charge, like that. So not this one here. So that's how you can also represent electric field, because actually electric field are continuous fields. So the magnitude of electric field is, in this representation, you have stronger electric field around here, because the concentration of the lines is more dense in this area than in this area. So the electric field here is much weaker than here. As you can also see another representation, so here you have longer magnitude near the charge, and then you gets smaller far away from the charge. So if you look at the charge three-dimensionally, you can see that it's like a ball radiating electric field in all directions, radial directions. And the number of lines that goes out of the charge, so if you have a charge here and you have outgoing 8 outgoing, for example, just an example, 8 outgoing field lines. So if you have a charge here that's triple than the original, then the field lines would also be triple. So here you have 8 field lines, so you will have 24 when you triple the charge. By the way, the field exists everywhere in space for as long as there is a source charge. So it doesn't just terminate in midair, but if there is an oppositely charged object there, then some of the electric field will be absorbed by that negatively charged object. But then again, the field is continuously radiated by charged particles. So you can feel it for as long as there is electric charge in space. The point, or a point, will always have that electric field being felt from the charge, neighboring charge. There's a property of electric field lines: they can never cross. So as you can see from here, you have positive charge and negative charge. So you have the electric field being released or radiated by a positive charge, and it's absorbed by the negative charge here. So you have that, and then you have, for example, here you have um, negative, I mean positive, both positive charges here. So these are the electric field that comes out of the positive charge, and the negative charge, if you have a negative charge here and here, then the electric field direction would just be opposite to what is shown here in the figure. And since electric fields are continuous fields, and if you set an area somewhere in space, then if there's a charge there that's present, then some fields would come out in that area. So if the area is shown here in this figure, it's like here, you can draw a normal line to that area, dA. So in this case, dA is a vector quantity. As you can see, A is bold. If you write it in by freehand, you have to write a vector above A. So in this case, there are electric fields that are, this surface area here could be an imaginary area. So if you have an area here, then some of the electric field would come out there in that area, and this electric field may not be normal to the plane of the area or of the surface. So in this case, you have an electric field that's in this direction, uniform direction. So there's an angle here that's angle theta that's measured between electric field and the dA. So in this case, you can write sort of flux. We denote flux in terms of phi, and we just put a subscript E such that we are able to recognize this as an electric flux. So that's the electric field that's coming out or coming in through an area. So if it's coming out of an area, that's of course positive, and if it's coming into the area, that is of course that's negative. But it also depends. It also depends where your direction of dA is. So if your dA is of course in this direction, then the flux would be also negative. So anyway, before going to the details of that later, we will define an electric flux. And electric flux is defined as the number of field lines passing through surface S. So in this case, you have this definition of the flux. So in this case, if you have a dA, if you have a very small area, then only a small flux comes out of that area, and that small flux is of course denoted by d phi E, and then you have that as E dot dA. This one is not a vector quantity, it's a scalar quantity, so you don't have to write any arrow above phi. And so if you integrate this, you also integrate this side on the surface area S. So you will have now the integral of this one is just, of course, phi e on the surface area S, and then you will have this definition. So if you want to get the total electric flux, then you have to integrate. So if you have a greater concentration of field lines, then the flux would be greater. So that means if you have a stronger electric field, then the flux would also be higher. And if you have a surface area that's measuring twice as big as one area, then the flux of that area would also be higher or greater, because it's proportional to the electric field and also of the area. By the way, the flux is only measured on the basis that the area vector is perpendicular to the surface, like here. It should always be perpendicular to the surface. So you must be careful choosing the surface. So for example, if you have an electric field here and your surface area is here, and so your dA would be in this direction. So in this case, you have a differential area that is perpendicular to the surface, and you have an electric field going here. The angle between them is 90, and that means cosine of 90 is 0, so there is no flux there. Actually, this is also equal to E dA cosine of theta, and this is the theta here. So if the theta here, the electric field is going in this direction, so the theta here is 90, so cosine 90 is just equal to 0. So you have to be careful. The flux through any closed surface is a measure of the total charge inside. This is the essence of the Gauss law. Let's check on the figure here. So if you have a charge that's inside a surface, say Q, so this charge will radiate electric field all over. So you can measure the total flux by what? You integrate E dot dA for the whole closed surface. So you can get the total flux of that. And by the way, look at this figure. You have here a surface, a closed surface. You have a charge Q and a charge 2Q. So these, both of these, they radiate electric field. So it's the 2Q will radiate an electric field here, and also radiate an electric field here. The Q will also radiate an electric field here and here as well. So both of the charge contribute to the flux that's coming out of the charge. The surface. And here you have a charge that is that is outside of the surface, and what happens is that the electric field here goes into the surface and then it also comes out. The net flux on the surface is 0, for example, because this one is supposed to be a negative flux and this one is supposed to be a positive flux, and these two flux are equal, so they just cancel. It goes inside the surface and then also comes out of the surface, so that will just cancel. But here you have a charge that's inside the surface, so both the electric field of the 2q will come out, and of course the q will also come out, so everything will come out. No one is going to, no electric field is coming in. So in this case it comes out, the electric field is positive. Usually when you have a closed surface, we can make an agreement that when you have a closed surface, the dA would always be positive if it's in the outside direction. This is positive, so this is now negative when you go inside. If your dA, that's your direction of your dA. But if you have an open surface, you have to just be consistent. So if you have a dA that's positive here, then your dA on the other side would be negative. So you just have to be careful with that. That's for open. But if you have a closed one, then your dA would always be positive for area vectors pointing outside of the surface. So for a point charge q at the origin, the flux E through the sphere of radius r is, we can compute that. So if you have a charge, say somewhere here, and then you enclose it with the sphere, so what is the total flux here? So if the charge would radiate electric field in all directions, so it's radiating electric field in all directions, radial direction. Here you will just have to enclose an imaginary surface. Say for example this surface here, you're enclosing the charge with an imaginary surface, and of course the charge is at the origin, and you must also coincide the center of the sphere to be at the origin as well, so that your electric field will be uniform on the imaginary surface. So your electric field is, if this is the magnitude of electric field here, the magnitude of electric field is also like that, in this direction, and also in this direction, also in that direction, and in that direction. But if you have a shifted position of the charge, then the electric fields here, the magnitude would not be equal. By the way, we are using here spherical coordinate system because it's much easier to solve this using spherical coordinate system than using the XYZ. So anyway, let's erase this figure, and the electric field given by the charge at the radius would be this 1 over 4 pi epsilon sub O q over r squared, and that's in the radial direction, as you have seen in the figure. And the dA, if you review in the previous lectures that we had, would just be r squared sine theta d theta d phi r hat as well, because the dA would be perpendicular to the surface. The surface is a sphere, so at any point you're getting the dA, that would always be perpendicular to that surface, so the direction would also be radial r. So if you dot this two quantities in the same direction, that would just give you 1. So in this case, you will have r squared canceling, and then you have in this case you will have double integral. You integrate through d theta and d phi, but the integral of d phi, since it's a sphere, the limit would just be 0 to 2 pi. So 0 to 2 pi would just be canceling the pi here, and of course sine theta d theta, when you integrate that would give you so the limit here for theta is, of course, since it's a sphere, it covers everything, so the limit would be 0 to pi. So the theta would be 0 to pi, and then your phi will be covering 0 to 2 pi. So that's the whole sphere if you rotate this curve. So this will give you 2, and then the 4 will cancel with the 2, and the other 2 will cancel with the 2 pi. So everything will be 1 over epsilon sub O times q. So what does this tell us? The integral, or the flux over a closed surface, is just equivalent to the charge inside that surface divided by epsilon sub O. So whatever charge is inside the surface, or the Gaussian surface, the surface could be imaginary or could be physically existent. So if you have a Q at the center, then if this Q is large, then the total flux would also be large. So in this case, you have found the relationship between the charge inside and the flux. So the flux is just equal to the total flux, is equal to Q over epsilon sub O. The example is dealing with a sphere, but actually you can use the result with a different surface. Even if it's an irregular closed surface containing a charge inside, then the flux would be, the total flux would be Q over E sub, or epsilon sub O. The flux through any surface enclosing the charge Q is Q over epsilon sub O, no matter what surface, sphere, cylinder, cube, whatever, they will give the same flux, which is equal to Q over epsilon sub O. So if you have many charges inside the surface, the total field is the vector sum of all the individual fields. so that your total flux would be due to the sum of the charges that's inside this the Gaussian surface or the physical surface. So you have to add all the Q, then you have dA here, the flux, I mean E dot dA. So to wrap it all up, we have the Gauss Law, and the Gauss Law says that for any closed surface, this is the Gauss Law. The flux would always be related to the charge enclosed, the total charge enclosed divided by epsilon sub O. We note that the radius 1 over r square cancelled with r square from here. From this one. And so it's now independent of r. Because if there was r, then we would have a problem with the integral, because r would have given 1 over r square an infinite value at the origin. So we have found this one. And so going back to the integral, we can use the divergence theorem such that we're able to write this integral here with this one. And in terms of the charge density, rho, in which if we integrate it with respect to the volume, we can get the total charge as well. So this one would have to be, since this one here is equal to Q enclosed over epsilon sub O, and you have therefore here you have a rho over epsilon sub O. Anyway, epsilon sub O is a constant, so you can put that into the integral, and this is now d tau. So if you look at this two here, this one and this one, you can artificially cancel the integral and the variable d tau to get this equal to rho of 0, rho over epsilon of 0. And this one is just the differential form of the Gauss law. The integral form is, of course, this one here. So you have this. So you have a problem here, 2.9. The electric field is given by this term here. So it would be easy to find the charge density rho. You just um, get the divergence of the electric field. The k there is just a constant, so you'll just derive the r cube through the spherical coordinates. Then you'd be arriving to the charge density. So much for those problems. We'll proceed with the divergence of the electric field. If we go back to equation 2.8, where the electric field is given by this one, we can get the divergence of the electric field by getting the divergence here and also on this side. But the divergence, this del here, is just interchangeable with the integral symbol. They commute, so you can put the del also inside of the integral. So you will have here, and by the way, previously we have calculated the divergence of this vector function to be just 4 pi delta function. In this case, you have a 3-dimensional delta function because you're doing the integral in 3-dimensional space. So you will have the divergence of E would be the same thing, because here you will have 4 pi will cancel with this, and the integral, because there's a presence of the Dirac delta there, the integral would just be rho, or density, rho of r. So it again gives you the differential form of the Gauss law. So again, if you integrate this part with respect to the volume d tau here, so this will just be again giving you the total charge enclosed divided by epsilon sub O, because this one and this one are equal, and this one is of course equal to that, and then you will have this one. We are now ready to apply the Gauss law. By the way, the Gauss law works efficiently with problems that has symmetry. Say for example, the sphere has a symmetry about an axis. A cylindrical surface would also have symmetry about an axis, and of course a pillbox would also have symmetry. So we can efficiently use Gauss law with Gaussian surface that are the closed Gaussian surface that has symmetry and a degree of symmetry. So as an example, we're going to find the electric field outside a uniformly charged solid sphere of radius r and total charge q. So we're having a solid sphere, and then we're going to find the electric field somewhere outside. So this sphere will have an electric field that's radiating in this direction, and of course here at this point the electric field would be here, and it is much longer because the point is near the sphere or the source charge. If it's far away, then if it's very far away from the sphere, the electric field would be very small. So we calculate the electric field. So here we have E dot dA. E dot dA here, this is equal to integral of E dA cosine theta. So by symmetry, if you enclose this solid sphere here with a Gaussian surface, which is also a sphere, so at any point on the surface, the electric field, so we'll just look at the components that are on the sideways. So here you have a component here, a component also there of the electric field directions in the Gaussian surface. But all of these field lines, or all of the electric field at measured at these points here, would have the same value. So that's a constant in terms of doing the integral. So we can put the magnitude of E out of the integral. By the way, this is now, I'm sorry, this is supposed to be, this one here is supposed to be ordinary numbers, not vectors. So it's just integral of E dA cosine theta. That's not equal to E dA cosine theta. This is wrong. So sorry for this one. So anyway, in this case also, you have, so for this point here, the electric field would be in this direction, but the area also, the dA will also be in this direction. So the theta, this is the dA, and your E would be this one. So the theta would just be 0. So cosine of 0 would be equal to 1. So you will have, so this one would be equal to 1. So everything, so you can put the magnitude of E outside because they are uniform in at any point on the surface of the Gaussian surface. So E would just be equal to, this integral would just be equal to this one here. The dA, the total surface area of the Gaussian surface, would be 4 pi r square. So this is now equal to Q over epsilon sub O, so that your electric field would be this one, which is the electric field that we would expect. So the remarkable feature here is that the field outside the sphere is exactly the same as it would have been if all the charge had been concentrated at the center of the sphere. So Gauss law is always true, but it's not always useful. We have to exploit the symmetry of the problem. So it would have been more difficult if the symmetry is not a sphere, a cylinder, or a cube. Symmetry is very crucial to the application of Gauss law. There are only 3 types of symmetry that works here. Spherical symmetry, and so in that case you will have to use the Gaussian surface concentric sphere, and for cylindrical symmetry the Gaussian surface would be coaxial cylinders, and then for plane symmetry the Gaussian pillbox spanning at the surface will do the trick. So the second and third symmetry would require infinitely long cylinders and planes extending to infinity to approximate the answer. So let's do an additional example. So here a long cylinder in this figure carries a charge density that is proportional to the distance from the axis, which is given by this one, for some constant k. So the S here is measured from the axis. So you have a cylinder, a cylindrical charge here, and the cylinder is that object that has axial symmetry. So in this case you're going to find the electric field inside this cylinder. So what I'm drawing inside is a Gaussian cylinder here. You have a bigger cylinder here that has a charge density that is proportional to the distance from the x-axis. So that means the charge density is not uniform throughout the volume of the cylinder. So as it goes out, the charge density gets more dense, gets denser. So here you will have to use the Gaussian or the Gauss Law to find the electric field. So electric field would be the integral of electric field that dA would be equal to 1 over epsilon sub O Q enclosed, but Q enclosed is of course rho d tau, because you don't have a uniform charge density, so your rho would be Ks and your d tau would be this one here. By the way, we make it a point that the z axis coincides with this one here, dz, such that the d phi is of course equal to, the limit of d phi here is 0 to 2 pi. That's for here, from 0 to 2 pi, the whole thing, the whole surface, the curved surface. And then you have dz extending from here to going there. And then you will have of course the S would be just the radius of the cylinder. So if you integrate d phi, it will give you 2 pi. The k will just come out of the integral. The dz, if you integrate that, the whole thing, the whole Gaussian surface will just have the length L, and then 0 to S for S prime squared ds prime, and so that would give you 3/2 pi k L s cubed. That's the electric field here inside. So let me just clear this figure. That's the electric field here. The electric field on this Gaussian surface inside. So if you look at it on a perspective where the circular surface is in front of you, the electric field would look like this. And they are the same magnitude at the surface, all in the same magnitude. Of course the direction is different, but the magnitude is the same. It will look like that, like a circular comb. So this is the, I'm sorry, this is just the Q enclosed. So you will have to calculate the electric field. I'm sorry, that was just the Q enclosed. Anyway, you can get the electric field by equating this to Q enclosed divided by epsilon sub O. So the Q enclosed would just be this part, and your electric field would then be equal to this one here, because the 2 pi will cancel here, and the s will also cancel, so you have s square, and then the l will also cancel, so you will have this electric field. So the dA also is also equal to the total surface area. By the way, if you look at it, you have a cylinder here, and the electric field is going, you're actually dealing with 3 surfaces. This one is surface 1, this one is surface 2, this one is surface 3. Surface 2 would have a dA that's going here, the dA of surface 2, and the surface 3 will have a dA that's going to this direction, but all the electric fields are going in this direction, and this is perpendicular to this dA of these 2 surfaces here. So the cosine of theta in this surface and in this surface would be 90, so it will not contribute to the total flux. Only this one, only this surface contributes to the total flux, this surface here. So that you actually have to chop the integral into 3 parts for S1, S2, and S3, but only S1 survives because that is the only surface that gives theta equal to 0, and S2 and S3 would give theta equal to 90, which is, of course, that's that, I mean, there's no flux that would come out there. So we're now moving to another example. An infinite plane carries a uniform surface charge sigma. Find its electric field. So find its electric field anywhere. So for example, we'll find the electric field at this point, for example, above the plane. So say for example, if you have this plane, you have to find the point, I mean, you have to find the electric field at this point, for example. So we have to draw a Gaussian pillbox, which is this one, and let's just make another view of the pillbox. So the pillbox here, the electric field goes out of the plane in this direction. So it goes out in this direction at the bottom and at the top in this direction. So the dA for the pillbox would be, for this surface you have the dA going here, the dA is also going here in that surface, and on the side you have the dA here and the dA here. So there are 1, 2, 3, 4 surfaces, but this surface and this one will contribute nothing to the flux because the angle between the electric field and the differential area is 90. So cosine of 90 is 0. So only this surface and this surface will contribute to the flux. And in that case also the theta is equal to 0. So again, you can chop the integral into 4 surfaces, and these 4 surfaces only two, from these 4 surfaces only 2 surfaces will contribute to the flux. So here, this surface area, this one here, will enclose a charge that is sigma times A, which is the area also of the, which is also the area here and also the area here. So that is the area of the pillbox at the top, and that's the same area at the bottom as well. So that's Q enclosed equals sigma A, and so your this one will be 1 sigma A over epsilon sub O. But then this one is, of course, you have S1 E dot dA plus the integral on S2 plus S3 plus S4, but 2 of the area does not contribute to the flux, and this one is the top surface and this one is the bottom surface. They're just equal because the electric field there going up and the dA is also going up. Here the electric field is going down and the dA is also going down. So, and of course the E are the same at the top and at the bottom, they're the same, and of course the dA would also be just the same. So we can compute by multiplying by 2 here and erasing this one, so that we will have at the top and bottom you have 2 times the total area would be 2A. The total area is A for the top and bottom, and then you have E to be a uniform. So you will have the total integral of E dot dA would be 2 AE. And so our electric field would be sigma over 2 epsilon sub O here. And the direction would be n hat, that means normal to the plane. So at the top and at the bottom would also be n hat. So this result is actually good for a plane that is, or a charge density that is extending to infinity. So wherever you go, or wherever point you measure the electric field, that would be the same if the charge density extends to infinity. But the direction of the electric field is, of course, at the top here and at the bottom to be here. How about for 2 infinite parallel planes carrying equal but opposite uniform charge densities? Find the electric field in each of the 3 regions to the left. First is to the left of both, second is between them, and to the right of both. In this case, you will have to make an analysis here. So you have 2 planes. These are the 2 planes. And you are going to draw the electric field between the two planes. The first plane here would give you an electric field going here, and of course here, and that is also the same electric field that comes out here. And the second plane, this one here, which is the negative charge, of course the negative charge would have opposite direction. You have a electric field going there and electric field going there also, and of course it's also the same electric field that goes out there, goes in this region. So what we can see from here is that this electric field is going in this direction, and in this one is going in that direction. They're opposite, so they will cancel because they have the same magnitude. This one will also cancel. What's left is that the electric field between the two plates, they go to the same direction, and then of course the total electric field then would be 2 times sigma over 2 epsilon sub O. In this case you have the x direction, so you have to cancel that one, and then you have an electric field going to the x direction, which is sigma over epsilon sub O. So the field is sigma over epsilon sub O and points to the right between the planes. In other places it would be 0 because the fields will cancel everywhere except between the plates. So you can solve some problems here. Let me just show you the problem. This will take time, but be careful and don't be careless, because in the analysis you will have to exploit symmetry, and then you will have to chop the surfaces, and just be careful. Don't hurry about solving this. Of course this will take time to solve, but just remember how they are being solved in the examples. So next session we'll have to deal with the curl of the electric field. So that's all for this session. I hope you've learned something, and just do the things that I had told you in the Google Forms. So watch out for the next series of the lecture.